Greetings, space cadets, and a warm welcome back to the Cosmic Detective Agency. Imagine a universe so vast and ancient, where the remnants of once brilliant stars continue to whisper secrets across unimaginable distances. Today, we're not just observing, we're diving headfirst into one of the universe's most perplexing enigmas, a mystery that challenges everything we thought we knew about stellar evolution and the very fabric of existence. We are talking about white dwarfs. These are not just any celestial bodies, but the dense, Earth-sized cores of stars that have lived out their fiery lives, shed their outer layers, and are theoretically supposed to be fading silently into the cold, dark oblivion of space. They are the stellar corpses, the cosmic ashes of what were once magnificent, luminous suns. Yet, in defiance of all expectations, these supposed embers of the cosmos are sending us signals, strange and inexplicable pulses that defy every known law of physics and astronomy. Picture this: billions of light years away, these dying stars are broadcasting messages, not in a language we understand, but in a code of light and energy that leaves our most brilliant minds utterly baffled. We're talking about 25 mind-bending, head-scratching "Are we alone?" signals that have left astronomers' world over scratching their heads in bewildered fascination. This isn't your average astronomy lesson where neatly packaged facts are presented for your consumption. Oh no, this is something far more profound. This is a journey into the uncharted territory of space mystery, a venture into the very heart of the unknown where the impossible just might be waiting for us silently, patiently for eons. The concept of a white dwarf, once thought to be a simple, predictable end state for a star, suddenly explodes into a frontier of cosmic puzzles, each signal a breadcrumb leading us deeper into an astonishing narrative that could redefine our place in the universe. What if these signals are not just random cosmic noise, but deliberate communications or perhaps manifestations of physics we have yet to even conceive? Buckle up, because this exploration will test the limits of our imagination and scientific understanding. We're about to venture into a realm where the lines between known science and astounding possibility blur, where every new piece of data only deepens the enigma. Each of these 25 unexplained signals from white dwarfs represents a profound challenge to our current cosmic models, a tantalizing hint that the universe is far stranger, far more alive with secrets than we ever dared to dream. This is an invitation to peer into the abyss of space, to confront the unknown, and to wonder what else lies hidden within the vast, silent stretches between the stars. Prepare to have your perceptions stretched, your curiosity ignited, and your understanding of the cosmos forever altered. Will these signals lead us to a new understanding of the universe, or perhaps to an encounter with something entirely unexpected? Let's find out together. Our journey begins with the very first unexplained phenomenon, what scientists have dubbed the hello from beyond burst. Consider a white dwarf, which is essentially a burnt-out star, a cosmic cinder silently drifting through the blackness of space. For all intents and purposes, it should be a picture of celestial tranquility. Yet, this particular white dwarf shattered that expectation by suddenly emitting a powerful, unprovoked burst of radio waves. This wasn't a gradual swell of energy, nor was it a subtle fluctuation in its usual output. Instead, it was an incredibly short, sharp burst, almost like a deliberate communication, a hello from across the cosmic void. What makes this signal so profoundly perplexing is its character. It wasn't a typical stellar flare, which are rapid increases in brightness often associated with magnetic activity on a star's surface. Nor was it a gravitational wobble caused by an orbiting companion. This was an isolated event, a sudden flash of radio energy that appeared without any discernible astrophysical precursor or accompanying phenomena that we understand. The iconic Arecibo Observatory, with its massive dish nestled in the natural karst landscape of Puerto Rico, was the instrument that first captured this astonishing signal. The surprise among the research team was palpable. This burst was so fleeting, so intense, and so unlike anything they had ever recorded from a white dwarf that initial reactions spanned a wide spectrum of possibilities. Some wondered if it was merely a technical glitch within the observatory's sensitive equipment, a phantom signal generated by an error in the system. Others speculated about terrestrial interference, perhaps a passing aircraft or a rogue radio transmission from Earth reflecting off the atmosphere. However, these more mundane explanations were systematically and meticulously ruled out after extensive analysis. Researchers painstakingly checked every possible source of error, cross-referencing data, and examining the observatory's operational logs. Each potential terrestrial or instrumental cause was dismissed, one by one, leaving them with an undeniable, genuine puzzle originating from the depths of interstellar space. The enduring mystery lies in the source of such a sudden, isolated outburst. How could a star supposedly in its twilight years, a remnant of a once active sun, generate such a powerful and singular radio emission without any known mechanism to explain it? White dwarfs are typically stable, cooling objects. They don't possess the dynamic, often violent, internal processes that characterize younger, more active stars. Their nuclear fusion engines have long since ceased, and their magnetic fields, while present, are generally thought to be far too weak to produce such an energetic burst as an isolated event. This signal challenges our fundamental understanding of stellar physics and the life cycle of stars. It forces us to ask if there are unknown processes at play within these stellar corpses, or if something entirely external, something currently beyond our scientific grasp, is influencing them. The hello from beyond burst isn't just an anomaly, it's a cosmic enigma that urges us to look deeper into the silent, cold remnants of dead stars. Moving beyond the perplexing hello from beyond burst, our cosmic journey brings us to the second unsettling signal, which scientists have cryptically named the wobbling light curve. Now, when we observe a star, we often measure its light over time to create what's called a light curve, which is essentially a graph showing how its brightness changes. For many stars, including some types of white dwarfs, these light curves can show variations or pulsations, much like a beating heart. These pulsations are usually predictable, following specific patterns that scientists can model and understand based on the star's internal structure and composition. However, this particular white dwarf defies all those established norms. Instead of a smooth, predictable rhythm that could be explained by known stellar physics, its light curve exhibits an unusual, irregular wobble. It's not just a subtle deviation, it's a chaotic dance, a jittery fluctuation that utterly baffles astronomers. This erratic behavior simply does not fit any of the known pulsational models. It's as if the star is performing an impromptu, offbeat jig, hinting at an unseen influence or perhaps an entirely new, unclassified type of stellar instability that we have yet to grasp. The sheer irregularity of this wobble is what makes it so profoundly mysterious. If it were a steady, repeating variation, we might attribute it to a known phenomenon like an orbiting planet or a binary companion. But its unpredictable nature, the way it seems to shift and change without any discernible pattern, suggests something far more complex. Imagine trying to predict the path of a leaf tossed in a turbulent wind, as opposed to a pendulum swinging steadily. That's the difference we're talking about here. Scientists have put forward a variety of hypotheses to explain this baffling behavior, each more intriguing than the last. Some theorize that the wobble could be caused by an unseen planetary companion, a planet orbiting so close to the white dwarf that its gravitational tug could subtly distort the star, causing its light output to fluctuate. Yet, even this explanation struggles to account for the utter chaos of the wobble. A planet would typically induce a more regular, periodic variation, not this seemingly random dance. Other, more exotic theories delve into the very fabric of the white dwarf itself. Could the wobble be a manifestation of strange, unknown forms of matter within its incredibly dense core? White dwarfs are stars where atoms are crushed beyond recognition and electrons are packed in a degenerate state. Perhaps there are processes or conditions within this extreme environment that create instabilities we've never encountered. There are also speculations about a highly dynamic yet undetected magnetic field interacting in unusual ways, or even the possibility of a subtle, continuous accretion of dark matter, causing disturbances that manifest as these light fluctuations. However, none of these proposed explanations fully or consistently account for the erratic nature of the wobble, leaving scientists to ponder if we are witnessing a phenomenon that requires a complete re-evaluation of our current understanding of stellar interiors, or even the fundamental laws governing gravity and matter in such extreme conditions. This wobbling light curve is not merely an observational quirk. It stands as a stark challenge to our existing models, compelling us to consider possibilities far beyond conventional astrophysics. Beyond the chaotic dance of the wobbling light curve, we now confront a third anomaly that directly challenges our fundamental understanding of stellar physics: the too-fast rotation. For decades, astronomers believed they had a firm grasp on the maximum speeds at which white dwarfs could spin, based on well-established principles of angular momentum conservation during stellar evolution. In essence, as a massive star collapses into a dense white dwarf, its rotation rate should increase, much like a spinning ice skater pulls in their arms to twirl faster. However, there are physical limits to this process. If a white dwarf spins too rapidly, the centrifugal force at its equator would overcome its powerful gravity, causing it to tear itself apart. Our models predicted a clear upper boundary for this rotational velocity, a cosmic speed limit beyond which these stellar remnants simply could not exist in a stable form. Yet, this particular white dwarf utterly shatters that theoretical mold. It has been observed spinning at an incredibly high velocity, a rate so extreme that it far exceeds every theoretical limit for its calculated mass. This isn't just a slight deviation, it's a profound violation of what our current understanding dictates is possible. The implications of such a discovery are nothing short of revolutionary. If our understanding of angular momentum conservation in stellar evolution is correct, then this white dwarf should not exist. It forces us to ask some very uncomfortable questions about the cosmic processes that lead to the formation of these stellar corpses. How could it have acquired such an excessive spin? One leading hypothesis suggests that this white dwarf might be the product of an incredibly efficient accretion process. This scenario would involve the white dwarf steadily siphoning matter, and thus angular momentum, from a nearby companion star over an extended period. Think of it like a cosmic whirlpool, gradually pulling in material and spinning faster and faster. While accretion can certainly increase a white dwarf's rotation, the challenge here is that the observed spin rate is so high that it would require an accretion process far more efficient and prolonged than any we have ever witnessed or theorized. It would demand a perfect alignment of conditions and almost surgical precision in the transfer of mass to achieve such an extreme velocity without causing the white dwarf to destabilize and shed its excess material. Alternatively, this too-fast rotation could hint that our models for stellar collapse itself are incomplete or fundamentally flawed. Perhaps there are unknown mechanisms at play during the death throes of a star, processes we haven't yet accounted for, that can impart significantly more angular momentum than our current equations predict. This would force a radical re-evaluation of how mass and spin are distributed in the remnants of massive stars, potentially rewriting entire chapters of astrophysics textbooks. It means delving into the very heart of how matter behaves under extreme gravitational conditions and how magnetic fields might interact with collapsing stellar material to preserve or even enhance their rotational speeds in ways we haven't conceived. This signal is not just an anomaly, it's a cosmic riddle compelling us to reconsider the delicate balance of forces that govern the life and death of stars, and to question whether our current understanding of stellar evolution is truly as comprehensive as we once believed. Beyond the perplexing rotations and erratic light curves, we now dive into the fourth baffling phenomenon, the unseen companion gravitational pull. Imagine a white dwarf appearing utterly alone in the vast cosmic expanse, yet its movements betray a profound secret. This isn't a subtle nudge or a gentle tug. It's a significant gravitational disturbance, a powerful pull that clearly indicates a massive, unseen companion is orbiting it. We have meticulously observed this white dwarf, tracking its orbital dance, and the evidence points unequivocally to something incredibly dense and heavy exerting a dominant gravitational influence. The mystery deepens because despite this undeniable pull, we simply cannot see what's causing it across any wavelength of the electromagnetic spectrum, from radio waves to X-rays and gamma rays. It remains stubbornly invisible, a phantom weight dictating the movements of its stellar partner. The intensity of this gravitational pull rules out many conventional explanations. It's too strong to be another smaller white dwarf or a gas giant planet, even a super Jupiter. The gravitational effect observed demands an object of immense mass, far greater than any known planetary body, and even surpassing the typical mass range of most stellar remnants visible to our telescopes. This invisible anchor is forcing astronomers to consider truly exotic possibilities, pushing the boundaries of astrophysical theory. Could it be a nascent dark matter halo, an accumulation of that mysterious, non-luminous substance that we believe makes up the vast majority of matter in the universe? Such a concentration of dark matter, if sufficiently dense and compact, might indeed exert the kind of gravitational influence we observe without emitting any detectable light or radiation. This idea, while fascinating, poses significant challenges, as forming such a localized, massive dark matter structure in orbit around a star is not something our current cosmological models easily explain. Another compelling, albeit unsettling, hypothesis is that this unseen companion is an elusive black hole. A stellar mass black hole, the collapsed remnant of a much larger star, would possess precisely the kind of extreme density and immense gravitational pull required to explain the observed perturbations, all while remaining optically invisible. The challenge then becomes detecting it directly. While black holes themselves do not emit light, they can reveal their presence through their gravitational effects on nearby matter, or by accreting gas from a companion star, creating telltale X-ray emissions. However, in this specific case, there's no evidence of such accretion or gas transfer, making it a truly dark black hole, if that's indeed what it is. This scenario would mean we're witnessing a rare type of binary system, one where a visible white dwarf orbits a silent, invisible cosmic void. Then there's the possibility of a rogue neutron star hiding in plain sight. Neutron stars are incredibly dense objects, even denser than white dwarfs, formed from the collapsed cores of massive stars after supernova explosions. They are tiny, often just a few miles across, and can be very dim unless they are actively accreting matter or emitting radiation as pulsars. A non-pulsing, isolated neutron star could easily go undetected if it's not actively interacting with its surroundings, yet still exert a powerful gravitational influence. The hunt for this invisible partner is an immense challenge, pushing the limits of our observational techniques. Astronomers are employing highly precise astrometry, meticulously measuring the exact positions and motions of the white dwarf in the sky over extended periods, looking for the telltale wobble in its proper motion caused by the gravitational dance with its hidden companion. They are also exploring advanced gravitational lensing techniques, attempting to detect any minute distortions in the light from background stars as they pass near the white dwarf system, which could be indicative of a massive, unseen object bending spacetime around it. Each new observation refines the orbital parameters of this invisible entity, deepening the mystery and forcing us to reconsider what silent, massive objects might truly be lurking unseen in the cosmic shadows. Beyond the silent pull of an unseen companion, we now encounter our fifth perplexing signal, the anomalous X-ray emission. This particular white dwarf is doing something truly extraordinary, something that flies in the face of all our conventional understanding. It's emitting X-rays, not just a faint glimmer, but a significant detectable flux of high-energy radiation. This might not sound strange at first glance until you consider what a white dwarf truly is. A stellar corpse, a remnant that should be steadily cooling down, radiating away its residual heat primarily through visible and ultraviolet light as it slowly fades into obscurity. Think of it like a cold ember long since extinguished, suddenly radiating intense heat. The amount of X-ray energy pouring from this particular white dwarf is far, far greater than what its measured surface temperature and known chemical composition would suggest. It's a profound contradiction, a blazing beacon where there should only be a gentle fading glow. This excess X-ray glow cannot be simply explained by standard thermal emission, the natural radiation given off by a hot object as it cools. If it were merely hot, its overall luminosity and spectral characteristics would be entirely different. Nor does it align with typical accretion disk activity, where a white dwarf might be siphoning material from a companion star, heating up that material as it spirals inward and generating X-rays in the process. While accretion disks are known sources of X-rays around some white dwarfs, the specific spectral signature and the absence of any visible or infrared evidence for a companion star or an active disk rule out this common explanation in this particular case. There's no smoking gun of infalling gas, no orbital dance with a partner, yet the X-rays persist strong and undeniable. This mysterious energy signature is forcing astronomers to consider a host of non-standard heating mechanisms, each more speculative than the last. Could there be an ongoing, unseen process within the white dwarf's incredibly dense interior? Perhaps some form of residual nuclear activity or exotic phase transition not accounted for in our models. Given the extreme conditions within a white dwarf where matter is compressed to densities far exceeding anything we can replicate on Earth, it's not entirely out of the question that unknown physics could be at play. Some theories propose that this anomalous X-ray emission might be generated by the interaction of exotic particles. Imagine dark matter, the elusive substance thought to permeate the universe, interacting with the white dwarf's extreme gravitational and magnetic fields, releasing energy in the form of X-rays as it passes through or accumulates within the star. This would be a groundbreaking discovery, offering a direct observational clue to the nature of dark matter itself. Another intriguing, albeit controversial, hypothesis involves the possibility of an internal magnetic dynamo effect, far more potent and sustained than anything we've previously observed in a cooling white dwarf. If such a dynamo could generate incredibly powerful and fluctuating magnetic fields, their interaction with the star's plasma could theoretically produce the observed X-rays. Yet, the energy required and the stability of such a process within a supposedly inert stellar remnant remain significant challenges to this idea. This white dwarf is a cosmic anomaly, a blazing X-ray mystery that compels us to look beyond established astrophysics. It suggests that there are heating mechanisms, or perhaps even entirely new forms of matter and energy interactions, operating in the extreme environments of dead stars that we have yet to even conceive. Its peculiar glow is a profound challenge, an open invitation to explore the unconventional physics that might govern the silent, cold remnants of cosmic giants. Following the perplexing X-ray emissions, we now move to the sixth baffling phenomenon, the sudden brightness spike. Picture a white dwarf, a celestial ember, a stellar remnant that should be cooling predictably and fading quietly over eons. It's supposed to be stable, its light output a stately, gradual decline. Yet, astronomers have observed instances where these supposedly inert stars suddenly, and without any discernible warning, brighten dramatically by several magnitudes. To give you some perspective, a change of even 1 magnitude represents a brightening of 2.5 times. So, several magnitudes mean these stars are becoming hundreds, even thousands of times brighter in an instant, only to dim back down within hours. This isn't a subtle flicker, it's a cosmic flashbulb, a brief, powerful burst of light that defies every known principle of conventional stellar physics. It's crucial to understand what this event is not. It's definitely not a nova, which is a far more violent and prolonged outburst caused by a white dwarf accreting hydrogen from a companion star, leading to a thermonuclear runaway on its surface. Novas are typically much brighter, last for days or weeks, and leave behind evidence of material ejection. Nor is it a flare, which is usually associated with magnetic activity on the surface of younger, more active stars, emitting energetic particles and often accompanied by X-ray or radio bursts. The sudden brightness spike is distinct. It's a single, powerful surge of visible light, an isolated event that appears to emanate from the white dwarf itself, lasting for only a few hours at most, and then returning to its previous serene state without any lasting changes in its spectrum or a detectable disruption of its outer layers. The sheer rapidity and intensity of these events, coupled with their isolated nature, are what make them so profoundly enigmatic. The primary puzzle is identifying what kind of internal instability or external interaction could possibly trigger such a rapid and dramatic change in luminosity from a star that is theoretically supposed to be inert. One hypothesis explores the idea of a sudden, deep rearrangement within the white dwarf's incredibly dense interior. Could there be a phase transition in the super-compressed material, perhaps a sudden crystallization or a shift in the degenerate electron gas that could release an enormous amount of energy in a very short period? Given the extreme pressures and densities inside these objects, where matter behaves unlike anything on Earth, such exotic internal processes aren't entirely beyond the realm of possibility. However, modeling such an event to produce the observed luminosity and short duration is incredibly challenging and would require a vast amount of previously unaccounted for internal energy to be released almost instantaneously. Another line of thought focuses on external triggers, even though no companion star has been detected for the white dwarfs exhibiting this phenomenon. Could a small, unseen object, perhaps a rogue asteroid or even a tiny planet, somehow collide with or graze the surface of the white dwarf at an incredibly high velocity? Such an impact could generate a temporary shockwave or superheat a localized region of the atmosphere, causing a dramatic but fleeting brightening. The challenge with this scenario is that the frequency and intensity of these spikes seem too regular for purely random impacts with interstellar debris, and the energy release observed would require a relatively significant impactor to generate such a dramatic increase in brightness. Furthermore, the absence of any lasting debris cloud or spectral signature of impact material makes this hypothesis difficult to confirm. The fleeting nature of these events makes them incredibly difficult to study in detail. By the time astronomers can point multiple telescopes at the target, the spike has often faded, leaving behind only tantalizing light curve data and an array of unanswered questions. This adds to their enigmatic allure, transforming them from simple observations into profound cosmic challenges, forcing us to rethink the very nature of these supposedly dead stars. Following the sudden brightness spikes, we now turn our attention to the seventh perplexing signal, the radio silence breaker. Imagine heading into a vast, silent library, a place where no sound is expected, and suddenly, from a seemingly empty corner, a clear, distinct melody begins to play. That's precisely what happened with this particular white dwarf. In a region of space where our astrophysical models predict absolute radio silence from these stellar remnants, one sprang to life, not with a faint, barely detectable whisper, but with a strong, discernible, repetitive pulse. This isn't just an anomaly, it utterly shatters a fundamental assumption about how white dwarfs generate radio waves. Historically, the thinking has been quite clear. For a white dwarf to emit radio waves, it typically requires very specific conditions. The most common scenario involves an extremely strong magnetic field, often millions or even billions of times stronger than Earth's, which can accelerate charged particles and produce synchrotron radiation, a type of radio emission. Alternatively, radio waves can be generated in close binary systems, where a white dwarf is accreting material from a companion star, creating shocks and powerful electromagnetic interactions. The key point is that both these scenarios come with a distinct set of observable characteristics, such as the presence of a strong magnetic field detectable through other means, like circularly polarized light, or signs of an orbiting companion and an accretion disk. What makes the radio silence breaker so profoundly baffling is that this white dwarf exhibits none of these expected characteristics. There's no evidence of an unusually strong magnetic field according to our current measurement techniques. It appears to be an isolated star with no detectable companion to feed an accretion disk. It simply does not fit the mold. This lone radio emitter is a cosmic anomaly, a rogue signal broadcasting from a place where it shouldn't exist, forcing scientists to fundamentally rethink the conditions under which these stellar remnants can generate detectable radio signals. How can a supposedly inert, isolated white dwarf, seemingly devoid of the usual mechanisms, produce such a clear and consistent radio pulse? One of the more intriguing, yet challenging, hypotheses suggests that we might be witnessing a previously unobserved interaction between the white dwarf and its surrounding interstellar medium. Perhaps there's an extremely tenuous, diffuse cloud of gas and dust that, under just the right, precise conditions of density and velocity, is being subtly perturbed by the white dwarf's gravitational or weak magnetic field. This interaction, though gentle, could theoretically create localized instabilities or very weak shocks that accelerate charged particles just enough to produce the observed radio pulses. However, the energy required for a discernible, repetitive pulse challenges this idea, as the interstellar medium in such regions is typically far too sparse to power such an emission. Another avenue of exploration delves into the exotic possibilities within the white dwarf itself. Could this be evidence of a very specific, rare type of internal oscillation that, though not powerful enough to cause significant brightening, somehow generates a localized, pulsating magnetic field that then produces radio waves? This would require a completely new understanding of the internal dynamics and magnetohydrodynamics of degenerate matter, pushing the boundaries of current stellar physics. It would imply that there are latent energies or processes within these dead stars that can manifest in unexpected ways, even without the external catalysts we typically rely on. Furthermore, there's the truly speculative notion that this emission could be a residual effect of the white dwarf's formation. Perhaps the collapse of its progenitor star left behind a unique, persistent configuration of trapped magnetic flux or highly energetic particles that, over eons, are slowly leaking energy in the form of these radio pulses, a kind of cosmic aftershock that our instruments are only now sensitive enough to detect. Whatever the cause, the radio silence breaker is more than just a peculiar observation. It's a profound challenge to our astrophysical rulebook, prompting a radical re-evaluation of what we thought was possible for these stellar ghosts. Beyond the baffling radio silence breaker, we now encounter our eighth profound mystery, the oscillating polarization. When we talk about polarized light, think of it like waves on the ocean. Unpolarized light has waves rippling in all directions, but polarized light has its waves vibrating predominantly in a single plane, or perhaps in a specific circular or elliptical pattern. Many celestial objects, including white dwarfs, can emit polarized light, especially if they possess strong magnetic fields or if their light passes through certain types of dust or gas. Scientists can measure this polarization to learn about the conditions present in the source or along the light's journey to Earth. However, the light from this particular white dwarf isn't just polarized, it shows a very unusual rhythmic oscillation in its polarization. This isn't a static alignment like a fixed compass needle. It's a dynamic, fluctuating pattern like a compass needle that suddenly starts swinging rhythmically back and forth, or even in complex geometric patterns for no immediately obvious reason. This constant, structured change in the light's polarization is incredibly difficult to attribute to any of our known magnetic field configurations or atmospheric effects within or around a white dwarf. The challenge here lies in the rhythmic nature of this oscillation. If the polarization were simply constant, we could perhaps map it to a stable, strong magnetic field or a particular alignment of atmospheric particles. But the fact that it changes predictably over time suggests a dynamic process at play. Our current models for white dwarf magnetic fields generally predict either a relatively stable dipolar field, much like a simple bar magnet, or perhaps more complex but still largely static multipolar fields. These models don't easily account for a sustained, periodic fluctuation in the light's polarization coming directly from the star's atmosphere or surface. It's as if something within the white dwarf is regularly twisting or altering the very fabric of its emitted light, a sort of cosmic light show that puzzles our most seasoned astrophysicists. This phenomenon isn't a simple alignment. It's a living, breathing pattern that hints at complex interactions between light itself, the star's magnetic fields, and potentially even the intricate, layered structure of the white dwarf's interior. Deciphering this polarized dance could unlock profound secrets about the white dwarf's internal dynamics, pushing the boundaries of our understanding of these ultra-dense objects. One leading hypothesis suggests that this oscillating polarization might be a direct manifestation of a pulsating or wobbling magnetic field within the white dwarf. Imagine a star's internal dynamo, the process that generates its magnetic field, not being perfectly stable, but instead undergoing subtle, rhythmic oscillations. If this were the case, the changes in the magnetic field's strength or orientation could directly influence the polarization of the light emitted from the star's surface. This would be a groundbreaking discovery, as it would imply a far more dynamic and less understood internal structure for white dwarfs than previously assumed, potentially involving complex magneto-hydrodynamic waves propagating through the degenerate matter. Alternatively, some scientists theorize that the oscillating polarization could be caused by the presence of a highly structured, perhaps even patchy or non-uniform, stellar atmosphere that is somehow rotating or oscillating in a complex manner. If different regions of the atmosphere had varying magnetic field strengths or chemical compositions, their combined effect could lead to the observed oscillating polarization as the star rotates or as these atmospheric features evolve. However, this would require a level of atmospheric complexity and dynamic behavior that is not typically associated with the relatively static, cooling atmospheres of white dwarfs. Yet another, more exotic possibility involves the interaction of the white dwarf with an as yet undetected, extremely close-in compact object that is inducing tidal stresses or magnetic field distortions which manifest in this precise oscillating pattern. This would demand an object of considerable mass, perhaps even another stellar remnant, orbiting the white dwarf in an incredibly tight, unique configuration that forces this light signature. Regardless of the ultimate cause, the oscillating polarization is a compelling challenge, urging us to peer deeper into the physics of how light, matter, and magnetic fields intertwine within the dense, enigmatic hearts of white dwarfs. Beyond the oscillating dance of polarized light, we confront our ninth profound mystery, the too cool for its age anomaly. Imagine discovering an ancient artifact that, by all accounts, should be cold to the touch, yet it retains a surprising warmth defying the passage of time. This is precisely the enigma presented by certain white dwarfs, According to our well-established models of stellar evolution, these stellar remnants should cool down at a predictable rate, progressively dimming and losing heat over billions of years. Think of them as cosmic embers slowly radiating away their residual energy as they age. We can, in theory, estimate a white dwarf's age based on its temperature and luminosity, using it as a kind of cosmic clock. Yet, this particular white dwarf simply doesn't fit the timeline. It appears significantly cooler than its estimated age would suggest, based on its supposed formation time and the standard cooling curves derived from our understanding of thermodynamics and nuclear physics. It's like finding a campfire that was lit billions of years ago and should be stone cold by now, yet it still emits a faint, perplexing warmth. This discrepancy is not a minor observational error. It's a profound challenge to our understanding of stellar cooling, cosmic timescales, and potentially even the fundamental age of our galaxy. The implications of this too cool for its age anomaly are far-reaching because white dwarfs are often used as cosmic chronometers, tools to date stellar populations and even entire galactic structures. If our cooling models are flawed, or if some unknown process is interfering with that cooling, then our cosmic clocks might be fundamentally inaccurate. This would necessitate a radical recalibration of our understanding of galactic history and the evolutionary timelines of star clusters. The primary question then becomes, what could be causing this persistent warmth? One intriguing hypothesis points to the possibility of an internal heating mechanism, something that is continuously, albeit subtly, replenishing the white dwarf's energy supply from within, preventing it from cooling down at the expected rate. This could involve exotic physics or processes not accounted for in standard stellar models. Consider the possibility of the decay of exotic particles. Our universe is filled with mysteries, and dark matter is one of the most profound. While we primarily understand dark matter through its gravitational influence, some theoretical models propose that certain types of dark matter particles might interact with ordinary matter in very subtle ways, or even decay into other, lighter particles, releasing tiny amounts of energy in the process. If a significant concentration of such hypothetical dark matter particles were to accumulate within the incredibly dense core of a white dwarf, their slow, continuous decay could provide a persistent, low-level heat source. This would be a groundbreaking discovery, offering a direct observational signature of dark matter interactions and opening an entirely new branch of astrophysics focused on how these elusive particles might influence stellar evolution. However, proving such a hypothesis is immensely difficult, as it requires detecting minute energy releases deep within a stellar object. Alternatively, the anomaly might hint at a fundamental flaw in our understanding of the cooling rates themselves. Perhaps the internal structure of white dwarfs is more complex than we realize, with properties of degenerate matter impacting heat transfer in ways our current equations don't fully capture. For instance, the crystallization process, where the carbon and oxygen ions within the white dwarf transition from a fluid state to a solid, crystalline lattice, is a known energy-releasing event. While this is accounted for in models, perhaps there are nuances to this process, or other phase transitions at extreme pressures and temperatures, that release more energy or sustain warmth for longer periods than previously thought. Or perhaps there's a previously unknown interaction between the white dwarf's strong magnetic field and its super-dense plasma, generating subtle internal heating through magnetic reconnection events or other magneto-hydrodynamic processes. Each of these explanations challenges a different pillar of our current astrophysical framework, compelling us to dive deeper into the extreme physics of these stellar remnants. The too cool for its age anomaly is not just a quirky observation. It's a ticking time bomb for our cosmic chronology, urging us to refine our understanding of the fundamental processes that govern the life and death of stars and the precise age of the cosmos itself. Beyond the baffling mystery of a white dwarf stubbornly refusing to cool down, we now plunge into an even more profound enigma: the high-energy neutrino shower. Imagine peering into the heart of a cosmic ghost, only to find it pulsing with some of the most elusive and energetic particles known to science. Neutrinos are often referred to as ghost particles because they interact so rarely with ordinary matter. Billions of them pass through your body every second, completely unnoticed. They are produced in prodigious quantities in the cores of active stars during supernova explosions and in other extreme cosmic events. The Sun, for instance, constantly showers us with low-energy neutrinos from its fusion reactions. Supernova, the catastrophic deaths of massive stars, are also known to unleash torrents of high-energy neutrinos, briefly outshining entire galaxies. But here's the mind-bending part. Our detectors on Earth have picked up unexpected bursts of these incredibly high-energy neutrinos, and the signals distinctly trace back to the direction of a distant, isolated white dwarf. This isn't just a handful of stray particles, it's a shower, an event indicating a significant, concentrated emission that defies all conventional astrophysical expectations for a stellar remnant of this type. A lone white dwarf, a supposedly inert stellar ember, should simply not be producing neutrinos, especially not in such quantities or at such extreme energy levels. Its nuclear furnace has long since been extinguished, and it lacks the violent, cataclysmic processes typically associated with neutrino production. This astonishing observation forces us to confront a profound challenge. What could possibly be generating such immensely energetic processes within or around a stellar corpse that is theoretically settling into a long, quiet fade? This signal opens up an entirely new window into extreme astrophysics, suggesting phenomena far beyond our current textbooks. The sheer energy of these neutrinos is a critical clue and a significant puzzle. Low-energy neutrinos are routine, but these are high-energy, implying a source capable of accelerating particles to incredible velocities, far exceeding what a white dwarf is generally thought to be capable of. One compelling, albeit speculative, theory suggests a link to incredibly efficient particle acceleration mechanisms within the white dwarf's immediate environment. Perhaps there are powerful, yet localized magnetic reconnection events occurring near the surface or within the atmosphere of the white dwarf, far more energetic and frequent than previously thought. These events could accelerate charged particles to relativistic speeds, and as these particles interact with the ambient plasma or magnetic fields, they could produce high-energy neutrinos through various decay processes or nuclear reactions. This would imply a dynamic, almost volatile, magnetic landscape on these supposedly placid stellar remnants. However, the sheer power required to generate such a neutrino shower through this mechanism remains a significant hurdle. Another, even more exotic possibility delves into the realm of dark matter. As we discussed with the too cool for its age anomaly, white dwarfs are incredibly dense, compact objects with immense gravitational wells. This makes them natural accumulation points for dark matter particles, if those particles exist and have even a tiny cross-section for interaction with ordinary matter. If certain types of dark matter particles are capable of annihilating or decaying when they come into close proximity, or when they are compressed to extreme densities, the core of a white dwarf could become a silent, clandestine laboratory for these interactions. The annihilation or decay products of such dark matter particles could include high-energy neutrinos, along with other particles that might be difficult to detect. Such a discovery would not only solve the mystery of the neutrino shower, but would also provide the first direct evidence for the existence and nature of dark matter, revolutionizing both particle physics and cosmology. The challenge, of course, is distinguishing a dark matter signal from other astrophysical processes, and the current models for dark matter interaction are still largely theoretical. This high-energy neutrino shower is not just another anomaly, it's a cosmic beacon hinting at profound, unknown physics at play in the universe's most extreme environments, compelling us to consider whether the silent ashes of stars might hold the key to unlocking some of the universe's most guarded secrets. Beyond the baffling high-energy neutrino showers, our journey into the unexplained brings us to the 11th enigma, the unaccounted-for mass loss. Imagine two cosmic dancers, two white dwarfs locked in a gravitational embrace, orbiting each other in a celestial ballet. For decades, astronomers have meticulously studied such binary systems, developing sophisticated models to predict how these stellar remnants interact. These models account for factors like tidal forces, where one star's gravity subtly deforms its companion, or stellar winds, streams of particles flowing from the stars themselves. Yet, in one particular binary white dwarf system, our most precise spectroscopic analyzers, which is like taking a cosmic fingerprint of a star's composition and behavior, reveal something truly bewildering. One of the white dwarfs in this pair is losing mass, not in a gentle trickle, but at a rate that simply cannot be explained by any known astrophysical mechanism. It's as if parts of the star are simply vanishing into thin air, leaving scientists scratching their heads and re-examining their most fundamental assumptions about stellar physics and binary evolution. The sheer discrepancy between the observed mass loss rate and what our models predict is profound. With tidal forces, we expect a certain amount of material to be gravitationally stripped away if the stars are close enough, especially if one is significantly more massive or if their orbits are eccentric. Stellar winds, while gradual, also contribute to mass loss, but even when factoring in the most extreme theoretical estimates for these phenomena, the white dwarf in question is shedding material at an accelerated pace that defies all calculations. It's like observing a perfectly sealed container slowly emptying, but there's no visible leak, no obvious point of egress for its contents. Where is this missing mass going? And more importantly, what unknown force is accelerating its departure, actively stripping away the star's material in such an unprecedented manner? This unexpected mass loss isn't just a minor statistical anomaly. It directly challenges our long-held models of binary star evolution, forcing us to consider processes and interactions that lie completely outside our current understanding. Several hypotheses have emerged to try and account for this cosmic vanishing act, each more intriguing than the last. One possibility involves an unseen third body within the system, perhaps a very small, extremely dense object like a rogue neutron star or even a mini black hole, whose highly elliptical orbit or close proximity is creating a complex, intermittent gravitational perturbation. This unseen interloper could be subtly, yet powerfully, tidally disrupting the white dwarf, accelerating its mass loss in ways our two-body models simply don't capture. The challenge, of course, is that such a third body remains entirely undetected, leaving its existence purely speculative. We would need to observe subtle changes in the binary's orbital period or complex wobbles in its movement to confirm such a scenario. Another, perhaps even more radical, hypothesis delves into the realm of exotic physics. Could there be an interaction with dark energy, the mysterious force believed to be causing the accelerating expansion of the universe? While dark energy is generally thought to operate on cosmological scales, perhaps under the extreme gravitational conditions within a binary white dwarf system, its localized effects could somehow manifest as a repulsive force, subtly pushing away the star's matter. This is highly speculative and would require a complete re-evaluation of our understanding of dark energy's properties. Alternatively, some scientists ponder whether the white dwarf itself is undergoing some form of exotic internal process, perhaps an incredibly slow but continuous phase transition, or a subtle release of latent energy that is somehow manifesting as mass ejection rather than simply cooling. This would imply an internal dynamic far more active than previously thought for these supposedly inert objects. The most challenging aspect of this unaccounted-for mass loss is the lack of a visible or detectable outflow of material. If the mass were being stripped away by a companion, we might expect to see it accreting onto that companion, producing flares or X-ray emissions. If it were a powerful stellar wind, we would detect specific spectral lines indicative of high-velocity outflows. Yet, the material seems to simply disappear, leaving no trace. This suggests that the missing mass might not be conventional baryonic matter at all, or it's being converted or ejected in a form that our current instruments cannot detect. This persistent anomaly demands a radical rethinking of the forces at play in some binary star systems, hinting at unknown gravitational interactions, exotic matter conversions, or even a subtle, continuous interaction with unforeseen cosmic phenomena. It's a profound puzzle, forcing astronomers to question if our cosmic accounting books are truly balanced. Beyond the puzzling case of an inexplicably shrinking white dwarf, we now delve into our 12th unexplainable observation, the infrared excess. Imagine a cosmic detective walking into what appears to be a cold, dark, abandoned house, only to find a furnace blazing with an intensity that defies belief. That's precisely the scenario with this particular white dwarf. According to all our established astrophysical principles, a white dwarf, being a long-dead star, should primarily emit light in the visible and ultraviolet wavelengths as its residual heat slowly radiates away. It should not be glowing intensely in the infrared. Yet, this specific white dwarf radiates significantly more infrared light than any standard model predicts for a star of its age and temperature. This isn't just a slight deviation, it's a profound, undeniable excess, a blazing anomaly that screams for an explanation. This intense infrared emission strongly suggests the presence of a substantial dust disk, a vast cloud of rocky and metallic debris swirling around the stellar remnant. It's like finding a cosmic construction site, or more ominously, a demolition zone, right where we expected only a quiet, cooling ember. The presence of dust around a white dwarf isn't entirely unprecedented. We know that some white dwarfs are observed to accrete planetary material, essentially swallowing the remnants of planets that once orbited them. This process is often signaled by spectral lines of heavy elements in the white dwarf's atmosphere, indicating that it has recently consumed rocky debris. The dust itself can be heated by the white dwarf's light, emitting infrared radiation that our telescopes can detect. However, what makes this particular infrared excess so profoundly puzzling is not just the sheer amount of infrared radiation, implying an extraordinarily massive and dense dust disk, but also the specific spectral signature of that infrared light. This signature, which acts like a unique fingerprint for the chemical composition and temperature of the dust, doesn't match what we typically see from simple, stable debris disks. It tells us that the dust is not uniformly distributed, nor is it sitting quietly in a well-behaved ring. Instead, it seems to indicate a highly dynamic, turbulent environment, potentially hinting at a very unusual and possibly ongoing process of planetary destruction, or even, paradoxically, some form of planetary formation in its immediate vicinity. The mystery deepens when we consider the implications of such an active and extensive dust disk around a supposedly dead star. If it's planetary destruction, it's occurring on a scale and with a ferocity that challenges our existing models of how planetary systems break apart. What force could be pulverizing an entire planetary body, or even multiple bodies, into such an enormous and persistent dust cloud around a white dwarf? Could it be intense tidal forces from a very close, unseen companion, constantly tearing apart celestial bodies? Or perhaps a series of catastrophic collisions between remaining planetary fragments, leading to a perpetual cascade of destruction? The sheer volume of dust suggests a continuous, rather than a single, isolated event, forcing us to consider a mechanism that actively replenishes this stellar debris field. This scenario paints a picture of a cosmic crime scene, where a planetary system is being brutally dismantled before our very eyes, its shattered remnants glowing eerily in the infrared. Conversely, some scientists have dared to propose an even more radical idea. What if this isn't a scene of destruction, but rather a cosmic nursery? A place where new planetary bodies are attempting to form, or perhaps reform, from the ashes of an older, vanished system. While this might seem counterintuitive around a stellar corpse, the presence of such a massive and active disk of raw materials, coupled with the unique spectral signature of the dust, could, under certain highly specific and theoretical conditions, allow for the gravitational accumulation of new, smaller bodies. This would redefine our understanding of planet formation, suggesting it can occur not just around young, active stars, but even in the melancholic aftermath of a star's death. This infrared excess is not merely an observational curiosity. It's a vibrant, confusing clue suggesting that the space around dead stars is far from inert, challenging us to decide whether we're witnessing a new kind of cosmic destruction or an unexpected rebirth, transforming our understanding of planetary system evolution. Beyond the fiery confusion of infrared excesses, we confront our 13th profound mystery, the unstable magnetic field. Imagine a cosmic compass needle, not merely pointing north, but wildly spinning, oscillating, and even flipping its poles with a chaotic abandon that utterly defies logic. This is precisely what astronomers have observed in a particular white dwarf, a star whose magnetic field is not static, as most are, but instead displays rapid, unpredictable fluctuations in both strength and polarity. Most magnetized white dwarfs exhibit strong but relatively stable magnetic fields, often hundreds or thousands of times stronger than the Sun's, remnants of their progenitor stars or generated during the white dwarf's formation. These fields are typically thought to be frozen in, meaning they decay extremely slowly over billions of years, gradually weakening as the star cools. Yet, this white dwarf behaves like a tempestuous magnetic dynamo, its field flaring, dimming, and even reversing direction on timescales that are shockingly short, from months to just a few years. This instability is unlike anything seen in other magnetized white dwarfs, and profoundly challenges our current theories of magnetic field generation, evolution, and decay in these incredibly dense, degenerate stars. It forces us to ask, what exotic internal processes could possibly be driving such a volatile magnetic environment in a star that should be a beacon of predictable, if extreme, physics? The sheer unpredictability of these fluctuations is what truly baffles researchers. If the changes were periodic, one might attribute them to a rotation effect, where we're simply seeing different magnetic poles as the star spins. But these aren't regular cycles. They are abrupt, seemingly random surges and dips in strength, coupled with shifts in the magnetic field's orientation that defy simple rotational explanations. This hints at something far more dynamic and internal, an active process within the white dwarf itself that is constantly reshaping its magnetic landscape. Current models of white dwarf magnetism largely assume that once the star forms, its magnetic field is essentially a fossil leftover, slowly fading over cosmic timescales. The idea of a white dwarf actively generating or regenerating such a powerful, unstable field is revolutionary and requires a complete re-evaluation of our understanding of magnetohydrodynamics in degenerate matter, where electrons are packed so closely that their behavior is governed by quantum mechanics rather than classical physics. It introduces the possibility that white dwarfs are not merely static cosmic anchors, but rather dynamic entities with internal processes far more complex and energetic than previously conceived. One leading hypothesis attempting to explain this unstable magnetic field delves into the intricate relationship between a white dwarf's internal structure and its magnetic activity. Could these rapid fluctuations be linked to internal convection, a process where hot material rises and cooler material sinks? While convection is common in active stars like our Sun, white dwarfs are generally thought to have very thin or non-existent convective zones due to their degenerate interiors and efficient cooling. However, if there are unexpected, perhaps transient, convective currents or turbulence within certain layers of the white dwarf, these movements of electrically conductive plasma could potentially generate or amplify magnetic fields through a dynamo-like process. This would be a completely new form of dynamo mechanism, operating under extreme conditions of density and pressure, perhaps driven by unique energy sources or phase transitions within the white dwarf's core that are not yet understood. Such a discovery would fundamentally alter our models of white dwarf interiors, suggesting they are far more complex and active than previously believed. Another intriguing, though equally challenging, possibility suggests that the magnetic instability might be a direct consequence of interaction with a yet undiscovered companion. Imagine a very close, perhaps very small and faint, object orbiting the white dwarf, whose gravitational or magnetic field is constantly perturbing the white dwarf, inducing tidal stresses or magnetic field reconnections that manifest as these rapid fluctuations. This companion could be a brown dwarf, a failed star too small to sustain fusion, or even a massive planet whose gravitational dance is somehow stirring up the white dwarf's internal magnetic processes. The challenge, of course, lies in the fact that such a companion remains completely undetected despite meticulous searches. Furthermore, the chaotic and unpredictable nature of the observed magnetic fluctuations doesn't perfectly align with the regular, periodic influences one might expect from a stable binary orbit. It implies a more dynamic and perhaps intermittent interaction, or a kind of feedback loop where the white dwarf's own internal response amplifies the external perturbation. The unstable magnetic field is more than just an anomaly. It's a profound challenge to our understanding of stellar magnetism, pushing the boundaries of what we thought was possible for these cosmic remnants and urging us to consider whether their internal fires are truly extinguished or merely smoldering in unexpected ways. Following the tumultuous magnetic fields, our 14th profound mystery reveals itself as the gamma-ray flicker. Imagine a quiet, darkened room where a supposedly extinguished candle occasionally, and without warning, emits a faint, high-pitched sizzle of pure energy. That's precisely what astronomers have observed, a faint, intermittent flicker of gamma rays emanating from a white dwarf that should, by all accounts, be utterly quiescent. Gamma rays represent the most energetic form of light in the universe, typically signifying incredibly violent and powerful phenomena. We usually associate them with the collapse of massive stars into black holes, the intense magnetic fields of rapidly spinning neutron stars, pulsars, or the collision of galaxies. They are the signature of cosmic violence on scales that dwarf anything we can comprehend on Earth. Yet this white dwarf, a relic star, the supposed peaceful end state of a sun-like star, is sporadically producing these high-energy photons, defying every known expectation. This isn't a continuous glow, it's a fleeting, almost ghost-like emission, a series of brief, powerful bursts that hint at transient, incredibly powerful events occurring on or near the white dwarf's surface, potentially involving particle acceleration to relativistic speeds. It's like discovering a quiet cemetery suddenly emitting flashes of lightning from a single, centuries-old tombstone. The presence of gamma rays from a white dwarf is already an anomaly, but their intermittent and sporadic nature makes this flicker even more puzzling. If it were a steady emission, we might try to attribute it to some lingering, stable process, however exotic. But the on-again, off-again nature of these gamma-ray bursts suggests something that is triggered, perhaps by an external event or an internal instability that reaches critical thresholds only occasionally. This kind of high-energy emission demands extreme conditions, far beyond what a cooling, inert white dwarf is supposed to provide. Generating gamma rays typically requires particles to be accelerated to speeds approaching that of light, then colliding with other particles or interacting with magnetic fields. The energy involved in even a faint gamma-ray flicker from a white dwarf is immense, defying conventional explanations for what are essentially dead stars. It forces us to consider mechanisms capable of generating and focusing incredible amounts of energy in an extraordinarily compact space, hinting at explosive micro-events that are currently beyond our grasp. One of the more compelling, yet highly speculative, hypotheses attempting to explain this gamma-ray flicker suggests the presence of ultra-strong, highly localized magnetic reconnection events surfacing sporadically on the white dwarf. Imagine the magnetic field lines on the white dwarf's surface twisting, stretching, and then suddenly snapping and reconfiguring, much like a rubber band breaking. This process, known as magnetic reconnection, is known to accelerate particles to extreme energies in solar flares and in the magnetospheres of active stars. However, for a white dwarf, the magnetic fields are generally considered to be static and stable, not dynamic enough to cause these kinds of violent, particle-accelerating outbursts. If such events are indeed occurring, it implies an incredibly complex and dynamic magnetic topology, perhaps with hidden, tangled field lines that periodically erupt, releasing bursts of energy in the form of gamma rays. This would suggest that the magnetic fields of white dwarfs are not merely fossilized remnants, but are actively rearranging and interacting in ways we do not yet comprehend, potentially influenced by the incredibly dense and conductive plasma within. Another, even more exotic possibility involves the accretion of very small, dense objects onto the white dwarf. While we discussed larger-scale accretion for the infrared excess, this scenario posits that tiny, high-velocity fragments, perhaps micro-asteroids or comets that survived the star's red giant phase, are occasionally impacting the white dwarf's surface. Given the immense gravitational field of a white dwarf, even a tiny speck of matter striking its surface at relativistic speeds could generate enough localized energy and shock waves to accelerate particles and produce a flash of gamma rays. The sporadic nature of the flicker would then be explained by the infrequent and random nature of these impacts. However, the energy conversion efficiency required for such an event to produce observable gamma rays from relatively small impactors is extremely high, and the lack of other associated phenomena like X-ray bursts or optical flares makes this explanation challenging to confirm. The gamma-ray flicker is not just a brief flash in the cosmic dark. It's a profound puzzle that compels us to re-examine the extreme physics that might still be at play within these supposedly quiescent stellar remnants, hinting that even in death, stars can still unleash powerful secrets. Moving on from the enigmatic gamma-ray flickers, we now arrive at our 15th profound mystery, the period glitch in pulsation. Imagine a cosmic clock ticking away with incredible precision for millennia, then suddenly, almost imperceptibly, skipping a beat or subtly altering its rhythm, only to resume its precise timing afterward. This is exactly what has been observed in a specific type of white dwarf, known as a pulsating white dwarf or a variable white dwarf. These stars are remarkable because their entire bodies oscillate, expanding and contracting with a regular, predictable rhythm, much like a giant celestial bell. These pulsations are driven by internal processes, specifically the ionization and recombination of hydrogen and helium in their outer layers, which trap and release energy, causing the star to subtly expand and contract. Scientists meticulously measure these pulsation periods, which can range from a few minutes to several hours, using them as incredibly sensitive probes of the white dwarf's internal structure, density, and composition. The precision of these stellar oscillations is truly astonishing, yet on rare and baffling occasions, one of these pulsating white dwarfs will experience a sudden, inexplicable change in its pulsation period, a phenomenon aptly dubbed a glitch. This isn't a gradual drift, it's an abrupt, instantaneous shift, a jolt to the star's fundamental rhythm. While glitches are a known phenomenon in neutron stars, particularly the rapidly spinning pulsars, their occurrence in white dwarfs presents a far greater and more perplexing challenge to our understanding. Pulsar glitches are typically attributed to sudden rearrangements in their incredibly dense, superfluid interiors, often involving the crust cracking as the star spins down. But white dwarfs are fundamentally different. They are much less dense, their crusts are not as rigid, and the internal physics that drives their pulsations is entirely distinct. The mechanisms that could cause such an abrupt and sudden shift in a white dwarf's pulsation period are poorly understood, prompting a scramble among astrophysicists to develop new theoretical frameworks. What could possibly cause such a powerful, instantaneous disturbance within a star that is essentially a cooling, inert giant crystal? This period glitch challenges our most sophisticated models of stellar oscillations and the internal dynamics of degenerate matter. It suggests that there are unknown forces or processes at play deep within these stellar remnants, capable of suddenly and dramatically altering their very fabric, making these supposedly peaceful objects far more dynamically unstable than we ever imagined. One of the leading hypotheses attempting to explain the period glitch in white dwarfs focuses on the incredibly complex and often tumultuous interaction between the star's solid, crystallized core and its more fluid outer layers. As a white dwarf cools over billions of years, its core gradually crystallizes, transitioning from a fluid plasma to a solid, ion lattice structure. This crystallization process is not uniform or perfectly smooth. It can create boundaries and interfaces between different states of matter within the star. It's theorized that a sudden, rapid rearrangement or release of latent energy at one of these boundaries, perhaps a starquake within the solid core, or a sudden change in the phase transition, could cause a cascade of internal adjustments that momentarily alter the star's moment of inertia, leading to the observed change in its pulsation period. Think of it like a figure skater suddenly shifting their body weight, causing a spontaneous change in their spin rate. However, the energy required for such a starquake to be sufficiently powerful to cause a perceptible glitch in a white dwarf's pulsation, and the precise conditions under which it might occur are still largely theoretical and difficult to model. It implies that the internal structure of white dwarfs is far from static, even in their old age, and might be undergoing constant, albeit slow, internal stress and adjustment. Another intriguing, though highly speculative, explanation for these period glitches involves the interaction of the white dwarf with external, unseen phenomena, or even with exotic forms of matter. Could a sudden, close encounter with a very small, dense, and currently undetectable object, perhaps a rogue planet or a compact dark matter clump, trigger a gravitational disturbance sufficient to momentarily alter the white dwarf's internal dynamics and its pulsation period? While such an event would need to be incredibly precise and powerful to cause an abrupt change rather than a gradual one, the absence of any visible external cause forces astronomers to consider such unlikely scenarios. Furthermore, some cutting-edge theories suggest that these glitches might be related to more fundamental, quantum mechanical effects within the degenerate electron gas that makes up the bulk of the white dwarf. Perhaps there are critical thresholds or phase transitions in this exotic matter that, when crossed, can lead to abrupt reconfigurations of the star's internal energy and momentum. Whatever the ultimate cause, the period glitch in white dwarf pulsations is a stark reminder that even in the seemingly well-understood realm of stellar remnants, the universe continues to surprise us with its intricate and often unpredictable behaviors, challenging us to push the boundaries of our scientific imagination. Beyond the mysterious period glitches, we now confront our 16th profound enigma, the isolated dust cloud. Imagine sailing through a perfectly clear, serene ocean, only to stumble upon a massive, dense fog bank seemingly appearing from nowhere with no land or weather system to explain its presence. This is precisely the cosmic puzzle presented by a particular white dwarf, which has been discovered enshrouded in a gigantic, isolated cloud of dust. This isn't just a faint wisp, it's a massive, opaque shroud detectable by how it dims the white dwarf's light and by its own infrared glow as it absorbs and re-emits the star's radiation. What makes this observation so utterly baffling is its context. This white dwarf is located far, far away from any known star-forming region, distant from dense nebulae where dust is naturally abundant, and it's certainly not part of an active planetary system that might be generating new debris. In fact, it resides in a relatively empty, quiescent part of the galaxy. This isolation fundamentally challenges our understanding of how such vast quantities of dust could possibly accumulate around a stellar remnant that should theoretically be too old and too inert to create or sustain such material. It's like finding a perfectly preserved, millennia-old mummy suddenly wrapped in a fresh, meticulously spun silken cocoon. The sheer volume and isolation of this dust cloud are what make it particularly perplexing. For this to simply be leftover debris from the white dwarf's original stellar formation, it would have had to persist for billions of years without dissipating or being swept away by stellar winds, which is highly improbable. Moreover, the dust itself has spectral characteristics that suggest it's relatively young, implying a recent formation event, not ancient leftovers. If it were a typical debris disk from the destruction of planets, as seen in some other white dwarfs, we would expect to see stronger evidence of heavy element pollution in the white dwarf's atmosphere and a more compact disk-like structure. Instead, we see a vast, diffuse cloud that doesn't fit the standard planetary destruction narrative, presenting a cosmic anomaly that forces us to question the very origins of matter in such unexpected places. This unexpected shroud around a supposedly solitary star raises a cascade of profound questions. Where did this dust come from, and by what mechanism did it form and localize around a star that has long since exhausted its nuclear fuel and shed its outer layers? One compelling, though highly speculative, hypothesis points to the possibility of an unseen, companion object playing a crucial and catastrophic role. Perhaps there's an extremely small, very faint or distant companion, a rogue brown dwarf, a massive planet, or even another stellar remnant that is undergoing a process of intense tidal disruption or collision. If this companion were a fragile, icy body from the outer reaches of the original stellar system, or a captured interstellar object, a close encounter with the white dwarf's gravitational field could tear it apart, generating a vast amount of dust and debris. The challenge with this scenario is that such a companion remains completely undetected, and the sheer scale and persistence of the dust cloud would require a truly massive, or perhaps repeated, catastrophic event. This would imply a hidden, violent history for this white dwarf, where even in its quiescent stage, it is capable of tearing apart nearby bodies. Another intriguing, and perhaps even more exotic, theory centers on the idea of highly unusual interstellar dust capture mechanisms. While white dwarfs are generally thought to be too small, and their gravitational reach too limited to efficiently sweep up significant amounts of diffuse interstellar dust, perhaps there are specific, unforeseen conditions at play. Could this white dwarf be passing through a particularly dense, yet otherwise undetectable, pocket of interstellar gas and dust that is somehow being gravitationally focused and accumulated around it? This focusing could be aided by a subtle, unseen magnetic field, or by peculiar hydrodynamic interactions that cause the dust to clump and settle around the star rather than simply passing by. This scenario would require a precise alignment of cosmic happenstance, but it forces us to reconsider the subtle ways in which dead stars might interact with the extremely tenuous matter that pervades interstellar space, transforming them from passive observers into active participants in the cosmic ecosystem, subtly molding their immediate environment in ways we have yet to fully comprehend. The isolated dust cloud is a profound mystery, a quiet cosmic ghost story that urges us to look beyond the obvious in search of hidden forces and unseen events. Beyond the curious riddle of isolated dust clouds, we now arrive at our 17th profound enigma, the non-thermal radio emission. Imagine walking into a blacksmith's forge. You expect to feel the heat, see the glowing metal, and hear the clang of the hammer, all signs of thermal energy, But what if instead you heard a high-pitched, piercing whine completely unassociated with heat coming from a seemingly cold anvil? That's precisely the cosmic puzzle presented by this particular white dwarf. According to our standard astrophysical understanding, white dwarfs primarily emit thermal radiation, which is simply the light and heat given off by a hot object as it cools down, and this applies to radio wavelengths as well. This emission originates from the star's inherent temperature. Hotter objects emit more energetic thermal radiation. Yet, this white dwarf broadcasts powerful radio signals that are distinctly non-thermal. This means the radiation isn't coming from the star's heat, but from processes that involve highly energetic, non-equilibrium physics, a kind of cosmic screech rather than a hum. This type of emission is typically observed from violent, energetic phenomena like the swirling supermassive black holes at the centers of active galactic nuclei, where jets of matter are flung out at near light speed, or from the explosive remnants of supernova, where shockwaves accelerate particles to incredible velocities. To detect it emanating from a white dwarf, a supposedly sedate stellar corpse, is truly baffling. It suggests an incredibly powerful, perhaps entirely unexpected, mechanism for accelerating charged particles in its immediate environment, turning this quiet ember into a miniature, self-contained cosmic accelerator. The fundamental distinction between thermal and non-thermal emission is key to understanding this mystery. Thermal emission is broad and continuous, a spectrum of light across many wavelengths directly proportional to temperature. Non-thermal emission, in contrast, is typically much narrower in its frequency range and originates from individual particles, usually electrons, being accelerated to relativistic speeds and then spiraling in a magnetic field. This process, known as synchrotron radiation, is incredibly efficient at producing radio waves, but it requires extreme conditions, very strong magnetic fields, and a population of highly energetic, free-moving electrons. The fact that this white dwarf is predominantly emitting in this non-thermal way, rather than the expected thermal glow, implies that it's generating or interacting with immensely powerful forces, far beyond what its seemingly quiescent nature would suggest. It's akin to finding an ordinary flashlight emitting a highly focused laser beam, seemingly from nowhere. This discrepancy forces us to rethink what kinds of energetic processes can exist around or even within these compact stellar remnants. One compelling hypothesis to explain this non-thermal radio emission centers on the white dwarf's interaction with a very unusual and highly dynamic magnetic field. While many white dwarfs have static fossil magnetic fields, the presence of non-thermal radio waves suggests a magnetic field that is not only extremely strong but also actively changing, perhaps through rapid reconnection events that accelerate particles to relativistic energies. Imagine a magnetic field that is constantly twisting, breaking, and reforming, flinging electrons outward at immense speeds. These energetic electrons, as they spiral through the magnetic field lines, would then emit the observed non-thermal radio waves. This would imply that the white dwarf's magnetic field is far more complex and active than previously thought, perhaps even being continuously regenerated or amplified by some unknown internal process or interaction with its external environment. However, the energy required to sustain such powerful and continuous non-thermal emission from what should be a cooling star is immense, leading to the question of what powers such a dynamic magnetic environment. Another intriguing, albeit speculative, possibility involves the white dwarf's interaction with an external source of matter or energy that we haven't identified. Could there be an extremely faint, undetected companion, perhaps a small, exotic object or even a rogue exoplanet, that is somehow shedding highly energetic particles or generating powerful shock waves as it interacts with the white dwarf's magnetic field or atmosphere? Or perhaps the non-thermal emission is the result of the white dwarf accreting interstellar plasma, not in a gentle, continuous flow, but in sporadic, violent events that trigger intense particle acceleration. This scenario demands a very specific kind of interaction, one that generates the necessary high-energy electrons without producing other, more conventional signs of accretion like X-ray flaring or a visible accretion disk. The non-thermal radio emission is not just a strange signal. It's a profound challenge to our understanding of the extreme physics that might be lurking in the cosmic corners we thought were familiar, urging us to explore the hidden power sources that might turn a dead star into a surprising source of cosmic energy. Beyond the powerful, non-thermal radio emissions, our journey into the unexplained takes us to the 18th baffling signal, the spectral line shift. Imagine a cosmic speedometer calibrated with exquisite precision, suddenly giving a reading that makes absolutely no sense. That's precisely what astronomers have observed in the light emanating from a particular white dwarf. When scientists analyze the light from a star, they spread it out into a spectrum, much like a prism separates sunlight into a rainbow. Within this spectrum, there are distinct dark lines called absorption lines, which are created when specific chemical elements in the star's atmosphere absorb light at characteristic wavelengths. The precise position of these lines tells us a great deal about the star, including its chemical composition and its velocity relative to us due to the Doppler effect. If a star is moving towards us, its spectral lines are shifted slightly towards the blue end of the spectrum. If it's moving away, they shift towards the red. This is a fundamental principle of astrophysics, as reliable as a well-oiled machine. However, in this specific white dwarf, the spectral lines exhibit a profound and unusual shift, one that points to a velocity that utterly defies all conventional explanations. It doesn't align with our detailed understanding of local galactic movements. We have precise maps of how stars typically orbit within our galaxy, and this white dwarf's measured speed is simply off the charts for its location. Furthermore, exhaustive searches have ruled out any binary interactions, meaning there's no unseen companion whose gravitational tug could be accelerating it to such extreme speeds. It's not part of a close binary system, nor is it being flung away from a past interaction with another star. The discrepancy is so significant that it has left scientists scratching their heads in bewildered frustration. This white dwarf is moving either far too fast or far too slow, or in a direction that simply doesn't fit the cosmic flow of its neighborhood. It's as if a car on a perfectly straight highway suddenly accelerated to impossible speeds without ever touching the gas pedal or being impacted by another vehicle. This spectral anomaly isn't just an oddity. It challenges our very understanding of how stellar objects move through the cosmos and forces us to consider whether an unseen force is at play, or if there's an exotic, uncatalogued interaction affecting its atmosphere that merely mimics a velocity shift. The primary puzzle posed by this spectral line shift is truly profound. What could possibly be imparting such an inexplicable acceleration to a lone white dwarf? One intriguing yet highly speculative hypothesis suggests that this white dwarf might be interacting with dark matter in a truly unique way. While dark matter is primarily understood through its gravitational influence, some theoretical models propose the existence of dark matter winds or highly localized concentrations of dark matter that could be passing through the galaxy, subtly nudging or even significantly accelerating celestial bodies. If this white dwarf is somehow encountering a particularly dense clump of dark matter, or if it has some unknown interaction cross-section with dark matter particles, this could potentially provide the mysterious accelerative force that accounts for the observed spectral line shift. This would be a groundbreaking discovery, offering direct evidence of dark matter's non-gravitational interactions, opening up a new frontier in both astrophysics and particle physics. However, such a scenario requires very specific and as yet unproven properties for dark matter. Alternatively, the anomaly might not be a true velocity shift at all, but rather a manifestation of exotic physics occurring within the white dwarf's atmosphere itself, subtly altering the spectral lines. Imagine an incredibly powerful, persistent, and highly localized electric or magnetic field within the white dwarf's outer layers, far more intense or dynamic than anything we've previously observed. Such extreme fields could, in theory, induce a Stark effect shift due to electric fields or a Zeeman effect splitting and shifting due to magnetic fields on the spectral lines, mimicking a Doppler shift. This would imply that the white dwarf's atmosphere is a chaotic laboratory of quantum mechanical interactions, influencing light in ways we don't fully understand. Another possibility is that the white dwarf is constantly accreting extremely tenuous but highly energetic interstellar plasma in a highly anisotropic manner, meaning it's pulling in material primarily from one direction. This continuous, uneven inflow of high-velocity particles could create a localized pressure or shock wave that subtly biases the spectral lines, creating the illusion of an unusual velocity. This would still point to a mysterious interaction with its immediate environment that we haven't yet identified. The spectral line shift is not merely a measurement discrepancy, it's a cosmic speed limit violation, challenging our fundamental understanding of stellar motion and pushing us to explore realms of physics that might be entirely new to our cosmic vocabulary. Beyond the baffling spectral shifts, our 19 mystery brings us to the rapid luminosity drop. Imagine a lighthouse beacon shining steadily across the dark ocean, suddenly, and for no apparent reason, dimming significantly for a brief period, then just as quickly returning to its full brightness. That's precisely what astronomers have observed with a particular white dwarf. This isn't a gradual fade, nor is it a subtle fluctuation. It's a pronounced temporary decrease in the star's light, much like an eclipse where a celestial body passes in front of another, temporarily blocking its light. The problem, however, is that our most powerful telescopes across every wavelength of the electromagnetic spectrum, from radio waves to X-rays, have detected no discernible companion, no visible object that could possibly be causing this sudden dimming. This absence of an occluding body is what makes this phenomenon so profoundly perplexing, challenging our fundamental understanding of both stellar behavior and the nature of unseen objects in space. It's as if an invisible hand is briefly passing in front of a cosmic lamp, leaving us to wonder about the nature of the unseen. The rapid luminosity drop is distinct from other types of stellar variability. It's not a pulsation, which would involve the star itself expanding and contracting. It's not a flare, which would be a sudden brightening. Instead, it's a clear, swift reduction in observed light, implying something is indeed moving between us and the white dwarf, or that the white dwarf itself is undergoing some unprecedented internal phenomenon causing it to briefly dim. The duration of these drops is also critical. They occur very rapidly, often lasting only minutes to a few hours, suggesting that whatever is causing the occultation, if it is an occultation, must be either very small or moving incredibly fast. This fleeting nature makes them exceedingly difficult to study in real time, often leaving astronomers to piece together the events from their recorded light curves, much like trying to understand a lightning strike from its lingering afterimage. The sheer depth of the dimming also rules out many mundane explanations, implying a substantial blockage of light. This isn't just a minor statistical anomaly. It implies a significant event or object whose nature remains entirely elusive. One leading hypothesis for these luminosity drops centers on the idea of occultation by a very small, extremely dark, and incredibly compact object. While we can't see it, its gravitational influence, if close enough, could be detected, but even that has proven difficult. If such an object were massive enough, like a small, rogue black hole or an isolated neutron star, it would certainly be dark. But to cause such a rapid and deep dimming of a white dwarf, it would have to pass almost directly in front of the star, incredibly close to its surface or along our line of sight. This would be a statistically rare event. Alternatively, it could be a smaller, non-luminous object like a brown dwarf or even a massive exoplanet that simply doesn't reflect enough light to be detected by current instruments. The challenge here is explaining why we haven't seen any gravitational interaction or even other light from such a body. The occulting object must then be exceptionally small and dense, passing across the face of the white dwarf so swiftly that it remains undetectable by other means. This would imply an entirely new category of dark objects that are not massive enough to be black holes, yet dense enough to cause such a profound visual disappearance. Another intriguing, though highly speculative, explanation for these sudden dimmings delves into the internal physics of the white dwarf itself, proposing a never-before-seen intrinsic phenomenon. Could the white dwarf briefly form a transient, opaque layer in its upper atmosphere, perhaps due to an exotic magnetic field interaction or a sudden, localized cooling event that momentarily causes a phase change in its atmospheric composition? While a white dwarf's atmosphere is generally thought to be stable and transparent, the extreme conditions of pressure and temperature could, in theory, harbor unknown complexities. Imagine a sudden, explosive release of gas from the white dwarf's interior that momentarily obscures its light, a kind of cosmic burp that briefly shrouds the star. Or perhaps a temporary structural rearrangement in the star's outer layers, a kind of starquake that momentarily alters its light-emitting surface. However, the precise mechanism for such an event, especially one that would be both rapid and temporary, remains elusive and would require entirely new physics beyond our current models. This rapid luminosity drop is not just a passing shadow. It's a profound cosmic riddle, compelling us to consider if there are invisible architects at play in the universe, or if the very stars themselves hold secrets that can momentarily make them disappear before our very eyes. Beyond the perplexing rapid luminosity drops, we now encounter our 20th profound mystery, the hydrogen-dominant atmosphere anomaly. Imagine a freshly brewed cup of coffee left out for hours. You'd expect the foam and lighter elements to dissipate, leaving a darker, denser liquid at the bottom. This is a crude analogy for what we expect in the atmosphere of a white dwarf. According to our well-established theories of stellar evolution and atmospheric physics, as a star like our Sun sheds its outer layers and becomes a white dwarf, the remaining light elements, primarily hydrogen and helium, should gradually sink below the surface due to their lighter atomic weight and the white dwarf's immense gravity. Heavier elements such as carbon, oxygen, and even trace metals, which are products of prior nuclear fusion, should then diffuse upwards, eventually dominating the visible atmospheric layers. This process, known as gravitational settling or diffusion, is a fundamental pillar of how we understand the composition and evolution of white dwarf atmospheres. Yet, in defiance of this settled theory, astronomers have identified a particular white dwarf that, despite its considerable age and apparent evolutionary path, retains an unusually high and persistent proportion of hydrogen in its atmosphere. This is not a star early in its white dwarf life. This is an ancient stellar remnant which should have long since exhibited a more stratified, helium or metal-rich surface. The sheer longevity of this hydrogen presence challenges everything we thought we knew about atmospheric diffusion and the final stages of stellar evolution. It's like finding that cup of coffee still topped with fresh, frothy foam hours after it should have vanished. The implications of this persistent hydrogen anomaly are truly profound. If our models of gravitational settling and diffusion are correct, and they have been remarkably successful in explaining the atmospheres of most white dwarfs, then this specific white dwarf should have developed a helium-rich or even carbon-rich photosphere by now. The fact that it hasn't means either our understanding of atmospheric physics under extreme gravity is incomplete, or there's an ongoing, active process that is continuously replenishing or somehow suspending the hydrogen against the relentless pull of gravity. It forces us to ask, is hydrogen somehow being prevented from sinking, or is it being constantly supplied from an external, unseen source? This is not a minor deviation. It's a direct contradiction of a fundamental expectation. hinting at a more dynamic and less understood interaction between dead stars and their cosmic surroundings. This anomaly could force a complete re-evaluation of how we interpret the spectral signatures of white dwarfs, potentially altering our understanding of their intrinsic properties and evolutionary timelines. One of the most compelling hypotheses put forward to explain this hydrogen-dominant atmosphere anomaly involves the continuous accretion of hydrogen-rich material from an unseen external source. Imagine an incredibly tenuous yet persistent stream of gas and dust flowing towards the white dwarf from a distant, perhaps very small and faint companion. This companion could be a brown dwarf, a failed star too small to ignite fusion, or even a large gas giant planet whose outer atmosphere is slowly being stripped away by the white dwarf's gravitational pull. If this material is rich in hydrogen, and if the accretion rate is just right, not so high as to cause a nova, but sufficient to constantly replenish the hydrogen in the white dwarf's atmosphere, it could explain the anomaly. The challenge with this scenario, however, is that such a companion remains completely undetected through conventional means, and the accretion process would need to be remarkably stable and continuous over very long timescales for the hydrogen to persist as observed. Furthermore, the absence of other signs of accretion, such as an accretion disk or X-ray emission that would typically accompany infalling material, makes this hypothesis difficult to confirm. It implies either a very subtle form of accretion or a companion that is extraordinarily elusive. Alternatively, the anomaly could hint at a truly revolutionary re-evaluation of our understanding of atmospheric settling itself. Perhaps under certain, as yet undiscovered conditions such as an unusually strong, globally uniform magnetic field, or a unique interplay of internal pulsations, the process of gravitational diffusion is significantly inhibited or even reversed. For example, some highly speculative theories propose that a white dwarf's magnetic field, if configured in a particular way, could create a magnetic levitation effect, subtly holding lighter hydrogen atoms aloft and preventing them from sinking into the denser layers below. This would require a very specific and stable magnetic field geometry, one that interacts with the atmospheric plasma in unprecedented ways. Or perhaps the white dwarf is undergoing a very subtle, continuous form of remixing, where internal convection currents, normally thought to be absent in hydrogen-deficient white dwarfs, are somehow reaching the surface and continuously stirring up deeper hydrogen-rich material. This would imply an internal dynamic far more active and complex than our current models suggest for these relatively stable, cooling stellar remnants. The hydrogen-dominant atmosphere anomaly is not just a peculiar atmospheric composition. It's a cosmic fingerprint revealing fundamental gaps in our knowledge, urging us to reconsider the forces that shape the very surface of these stellar ghosts and potentially challenging the universal applicability of even our most trusted laws of stellar physics. Beyond the baffling hydrogen mystery, we now confront our 21st profound enigma, the unexplained flare-up. Imagine a quiescent volcano, long dormant, unexpectedly erupting with tremendous force and then settling back into silence, only to repeat this unpredictable performance years later without any apparent seismic trigger. That's precisely what astronomers have observed with a particular white dwarf. This isn't a continuous blaze or a predictable pulse. It's a dramatic, rapid, and apparently spontaneous increase in luminosity, releasing an enormous amount of energy in a very short period. What makes this phenomenon so profoundly baffling is that these flare-ups are distinct from any known types of stellar explosions or variability. They are not recurring nova, which are thermonuclear explosions on the surface of a white dwarf caused by the accretion of hydrogen from a companion star. Nova follow a clear pattern of accretion, explosion, and then a return to quiescence, often repeating after a predictable accumulation of matter. Nor are these events supernova explosions, which represent the complete destruction of a star. Instead, these unexplained flare-ups are unique. They are singular, powerful bursts of light, often hundreds or thousands of times brighter than the white dwarf's normal luminosity, lasting for hours or days, and then inexplicably fading, leaving the white dwarf seemingly unchanged in its long-term characteristics. This behavior utterly defies current models of stellar instability for these supposedly stable, inert stellar remnants. It forces us to ask what internal or external trigger could possibly be responsible for these sudden, powerful detonations from a star that should be cooling quietly into cosmic oblivion. The challenge posed by these unexplained flare-ups is multifaceted. Firstly, the sheer energy released during these events is immense, demanding a powerful, efficient mechanism. Secondly, their unpredictable nature and lack of an obvious external trigger make them incredibly difficult to forecast or study in real time. By the time astronomers detect one, it's often already underway or beginning to fade. Thirdly, and perhaps most importantly, the white dwarf appears to recover completely after each flare-up, returning to its pre-flare luminosity and spectral characteristics without any apparent damage or significant mass loss, unlike a nova which often sheds material. This suggests a repeatable yet unknown process. It's like a cosmic pressure valve that occasionally bursts open, releases built-up energy, and then seals itself back up, waiting for the next inexplicable release. This behavior fundamentally challenges our understanding of the delicate balance of forces and energies within these compact objects, suggesting that white dwarfs might harbor far more dynamic and potentially explosive internal mechanisms than previously assumed. It also forces us to consider the possibility of extremely subtle, perhaps transient, interactions with their environment that are currently beyond our detection capabilities. One compelling, albeit highly speculative, hypothesis attempts to explain these unexplained flare-ups by invoking an exotic internal energy source within the white dwarf. Could the white dwarf's incredibly dense interior, where matter is compressed to densities far exceeding anything on Earth, be undergoing some form of exotic phase transition? Perhaps a fraction of the white dwarf's core material, under extreme pressure and temperature, briefly shifts into a super-dense, energy-releasing state, a kind of ultra-fast crystallization or a localized quantum mechanical rearrangement, releasing a torrent of energy that manifests as a flare-up. This would imply that the internal structure of white dwarfs is far more complex and capable of storing immense amounts of latent energy than our current models predict. Such an event would be akin to a very localized internal thermonuclear flash that doesn't involve external accretion but rather a sudden release of stored energy from the degenerate matter itself. However, the precise physics required for such a rapid, repeatable, and non-destructive internal energy release remains largely theoretical and would necessitate a complete re-evaluation of the thermodynamics and equation of state for matter under such extreme conditions. Another intriguing line of inquiry explores the possibility of an external yet undetected trigger. Could the white dwarf be experiencing highly localized and transient accretion events from extremely diffuse interstellar material, or even a continuous but very low-level stream of dark matter particles? If such material were to accumulate in very specific regions on the white dwarf's surface, or interact with its extreme gravitational and magnetic fields in unusual ways, it might trigger localized, powerful instabilities. For instance, very specific types of dark matter interactions, or even the sporadic accumulation of dark energy in a concentrated form, could potentially trigger miniature nuclear reactions or magnetic field reconnections that lead to these energetic outbursts without the need for a companion star or a visible accretion disk. The challenge with this scenario is that the energy required for these flare-ups would necessitate an accretion or interaction rate far beyond what is typically expected for an isolated white dwarf traversing the sparse interstellar medium. Furthermore, the lack of any discernible precursor events or follow-up emissions like X-rays or specific spectral lines indicating infalling material makes these external trigger hypotheses difficult to confirm. The unexplained flare-up is not just a bright flash in the cosmic dark. It's a profound cosmic riddle that challenges our most fundamental assumptions about the stability and internal dynamics of dead stars, pushing us to consider whether they are truly quiescent or merely harboring explosive secrets waiting for the right, inexplicable moment to unleash their fury. Beyond the inexplicable flare-ups, we now confront our 22nd profound mystery, the peculiar composition signature. Imagine a cosmic autopsy where scientists meticulously examine the chemical fingerprint of a dead star, expecting to find the familiar remnants of hydrogen, helium, carbon, and oxygen, elements forged in stellar fires. Yet, in one particular white dwarf, our most precise spectroscopic analysis, which analyzes the light emitted or absorbed by an object to determine its chemical makeup, has revealed something truly astonishing. Elements present in its atmosphere that simply shouldn't be there, or, if present, in proportions that are so wildly unusual they defy every known principle of stellar nucleosynthesis. Basic stellar evolution, it's like digging up an ancient fossil and finding it infused with a rare, earth-bound mineral that couldn't possibly have existed at the time or place the fossil formed. This anomaly forces a fundamental re-evaluation of not only the white dwarf's life story, but also the broader cosmic processes that might introduce such unexpected chemical ingredients into seemingly isolated stellar remnants. It's a chemical riddle etched in starlight, hinting at hidden cosmic processes or even an entirely unique, uncatalogued formation history. The presence of these anomalous elements, or their highly skewed proportions, challenges a cornerstone of astrophysics, our understanding of how stars forge elements and how those elements are distributed within a star's structure, especially as it evolves into a white dwarf. During a star's active life, nuclear fusion creates heavier elements from lighter ones, a process called nucleosynthesis. When a star dies and becomes a white dwarf, its atmosphere is usually dominated by hydrogen or helium, with heavier elements settling gravitationally into the core over time. If heavier elements are seen on the surface, it often implies recent accretion of planetary debris. However, the elements found in this peculiar white dwarf are not typical planetary building blocks in the expected ratios, nor do they align with elements that would normally be dredged up from the white dwarf's interior. Some of these elements are exceedingly rare, while others are present in such overabundance that it suggests a source entirely different from what we understand about stellar death or planetary consumption. This startling chemical signature means either the white dwarf recently absorbed some truly exotic material, or its entire formation pathway was radically different from anything predicted by our models, hinting at a hidden cosmic process or an interaction with something truly alien to our current astrophysical understanding. One compelling hypothesis to explain this peculiar composition signature suggests the recent and unusual accretion of exotic material, perhaps from an interstellar object. Imagine the white dwarf silently drifting through space, encountering a rogue planet or a fragment of a planetary body that originated from an entirely different stellar system, perhaps even a system with a radically different chemical environment. If this interstellar visitor were rich in these peculiar elements, and if it were then tidally disrupted and accreted by the white dwarf, it could leave behind the observed anomalous spectral fingerprint. This would imply that the white dwarf is acting like a cosmic vacuum cleaner, occasionally pulling in and consuming material that has traversed vast cosmic distances, carrying with it the chemical signatures of other star-forming environments. The challenge, of course, is that such accretion events are inherently difficult to observe directly, and the specific chemical makeup of theoretical interstellar objects is largely unknown, making it difficult to confirm this scenario. Furthermore, the sheer abundance of some elements might require a very large or a very concentrated source of these specific materials, pushing the boundaries of what we expect to encounter in interstellar space. Another, perhaps even more radical, explanation delves into the white dwarf's unique formation history. Could this white dwarf be the remnant of a progenitor star that itself had an incredibly unusual chemical composition, perhaps born in an environment vastly different from our own Milky Way galaxy, or formed from pristine, first-generation matter in the early universe before heavier elements were widely distributed? This would imply that the anomalous elements are not accreted but are intrinsic to the star itself. However, for such elements to remain in the white dwarf's atmosphere over billions of years, defying gravitational settling, would require a continuous, as yet unknown mixing process or a complete re-evaluation of how diffusion works in these stars. Alternatively, some truly exotic theoretical models propose that this white dwarf could be the product of an extremely rare and violent stellar merger, perhaps between two highly unusual stars, where the extreme conditions of the merger process somehow produced or preserved these peculiar elemental ratios. This would mean that the white dwarf is a kind of cosmic chimera, carrying the chemical scars of a unique and cataclysmic birth. The peculiar composition signature is not just a scientific curiosity, it's a profound chemical puzzle, challenging our cosmic inventory and urging us to consider whether the universe holds many more exotic ingredients and formation pathways than our current models dare to dream of. Beyond the peculiar chemical fingerprints left by unknown cosmic interactions, we now face our 23rd profound enigma, the asymmetrical light curve. Imagine a perfectly balanced spherical lamp uniformly radiating light in every direction. You'd expect its brightness to appear constant, no matter how it's spinning, unless an external object passes in front of it. Yet, for a particular white dwarf, one that appears utterly isolated in the vast cosmic expanse, its light behaves in a baffling, lopsided manner. Its light curve, the precise measurement of its brightness over time, displays an unexpected and persistent asymmetry. It's not a subtle tilt, it's a pronounced, uneven glow where one side consistently appears brighter or dimmer than the other, or where its variations are not symmetrically distributed as they should be. This isn't the kind of regular, periodic pulsation we've discussed before, where the entire star expands and contracts rhythmically. Nor can it be explained by simple stellar rotation alone, which would typically produce predictable, symmetrical changes as different parts of the stellar surface come into view. The observed asymmetry is profound, suggesting that this cosmic lamp is somehow flawed, emitting light unevenly from its surface or being subtly, yet powerfully, perturbed by something unseen. This fundamentally challenges our assumption that white dwarfs are uniformly cooling, spherical bodies, forcing us to ask, what could possibly be causing such a lopsided glow from a star that should be radiating its residual heat symmetrically? The central puzzle of this asymmetrical light curve lies in its persistent, non-uniform nature. If the asymmetry were due to a large, dark spot on the star's surface, we would expect to see a single, recurring dip in brightness as that spot rotated into and out of view. Similarly, if it were a very strong, localized magnetic field, it might alter light emission, but usually in a more localized and predictable way. The observed asymmetry is far more complex, a subtle yet profound deviation from expected uniformity that suggests a more fundamental imbalance. It's like watching a perfectly round, spinning top that, instead of wobbling symmetrically, consistently dips lower on one side. This challenges our models of a white dwarf's outer layers and surface composition, implying either an uneven distribution of material, a permanently warped shape, or an unseen, asymmetrical perturbation affecting its light output that is not easily explained by simple physics. The nature of the asymmetry is also key. It's not just a difference in overall brightness, but often involves subtle shifts in the shape of the light curve itself, indicating complex interactions at play within the star's atmosphere or immediate vicinity. This makes it a far more intricate problem than a mere surface feature would suggest, compelling astronomers to consider more exotic and dynamic explanations. One compelling hypothesis attempting to unravel this mystery points to the possibility of an ongoing, highly localized, and perhaps asymmetric accretion of interstellar material onto the white dwarf. Imagine the white dwarf silently sweeping through the sparse interstellar medium, but instead of uniformly drawing in material from all directions, it's encountering a particularly dense, perhaps clumpy, stream of gas and dust coming predominantly from one side. As this material rains down onto one hemisphere of the white dwarf, it could generate localized heating, cause subtle changes in the atmospheric opacity, or even create temporary, uneven magnetic disturbances. This uneven accretion would then result in an asymmetrical light signature, as one side of the star experiences higher temperatures or different atmospheric conditions than the other. The challenge with this scenario is that the interstellar medium is generally thought to be incredibly diffuse, and for such a process to continuously generate such a noticeable and persistent asymmetry would require a remarkably specific and sustained flow of material, potentially from a source that remains unseen or is far away. Furthermore, the absence of other, more conventional signs of accretion, such as strong X-ray emissions or a visible accretion disk, adds to the complexity of this explanation. Another intriguing, though highly speculative, theory delves into the white dwarf's interior dynamics. Could the asymmetry be a manifestation of a gravitational quadrupole moment, meaning the white dwarf isn't perfectly spherical but is slightly deformed, perhaps due to an extremely strong internal and non-uniform magnetic field, or even a subtle internal rotation that isn't perfectly aligned with its observable spin? Such an internal warp, if stable and sustained, could cause one side of the star to consistently be slightly closer to us, or to have a subtly different effective temperature or surface gravity, leading to an asymmetrical light output. This would imply that the white dwarf is not the perfectly spherical object we often assume, but has a subtle, persistent deviation from perfect symmetry, possibly due to extreme internal pressures or processes we haven't yet accounted for in our models of degenerate matter. This would force a re-evaluation of the white dwarf's structural stability. Alternatively, some scientists have considered the possibility of an extremely close, yet unseen, compact object, like a very small neutron star or even a mini black hole, whose gravitational field is so powerful and its orbit so precise that it distorts the white dwarf itself, or creates complex, asymmetrical tidal stresses that manifest as uneven light emission. This would require an incredibly unique and stable binary configuration that has so far eluded direct detection. The asymmetrical light curve is not just a peculiar blink in the cosmic dark. It's a profound challenge to our understanding of stellar symmetry and the hidden forces that might subtly reshape the very light emanating from these enigmatic stellar remnants. Beyond the puzzling asymmetrical glows, we now arrive at our 24th profound mystery, the sudden temperature increase. Imagine a perfectly working refrigerator. You expect it to remain cold, steadily maintaining its low temperature. Now visualize one that, over time, without any intervention, begins to subtly get warmer, defying its very design. That's precisely the startling anomaly astronomers have detected in a particular white dwarf. According to every established principle of astrophysics, a white dwarf is a stellar corpse, a remnant that has exhausted its nuclear fuel and is supposed to be in a perpetual state of cooling. Its journey through cosmic time is a slow, gradual fade, radiating away its residual heat as it progresses towards the ultimate fate of becoming a cold, dark black dwarf. Yet, this specific white dwarf stubbornly defies this fundamental expectation. Careful, repeated measurements of its light, analyzed through precise spectroscopic techniques, reveal a measurable, albeit slight, increase in its surface temperature over a period of years. This isn't a statistical fluke. It's a consistent, undeniable warming trend from an object that should be doing the exact opposite. This observation challenges the very definition of a white dwarf as a passively cooling stellar remnant, forcing us to fundamentally re-evaluate our understanding of stellar thermodynamics and the long-term evolution of dead stars. It's like finding an ember decades after a fire that should be stone cold, instead subtly growing warmer. The implications of this sudden temperature increase are nothing short of revolutionary, striking at the core of our understanding of stellar death. If white dwarfs are indeed just inert, cooling objects, then a sustained temperature rise, even a minor one, is simply impossible without an external energy input or an unforeseen internal process. This anomaly demands an answer to a critical question. Is this white dwarf secretly undergoing a slow, internal energy release, a hidden furnace rekindling itself against all odds, or is there an external heating source currently beyond our detection, subtly influencing its evolution and injecting energy into its frigid core? The subtlety of the temperature increase makes it even more perplexing. It's not a violent, sudden outburst that would point to a cataclysmic event. Instead, it's a gentle, persistent warming, suggesting a continuous, low-level energy generation or absorption that is incredibly efficient and incredibly difficult to detect. This phenomenon suggests that our cosmic clocks, based on the cooling rates of white dwarfs, might be fundamentally flawed for some stars, potentially altering our chronological understanding of galactic history. It also brings into question whether the dead status of white dwarfs is as absolute as we once believed, hinting at a more dynamic and perhaps even active existence than previously theorized. One of the most intriguing yet speculative hypotheses put forth to explain this temperature anomaly is the idea that the white dwarf is undergoing a slow, continuous internal energy release, perhaps driven by exotic physics. Could there be a form of dark matter annihilation occurring within its incredibly dense core? As we've discussed, white dwarfs are gravitational wells where dark matter particles, if they exist and interact with each other, might accumulate to high densities. If a specific type of dark matter particle were to annihilate or decay upon reaching a certain density or interacting with the white dwarf's ordinary matter, it could release a small but steady stream of energy, subtly warming the star from within. This would be a monumental discovery, providing direct evidence for dark matter and revealing unexpected properties of these elusive particles. However, the exact properties of dark matter are still unknown, making this hypothesis difficult to prove or refute without further observational evidence. Another possibility involves the crystallization process within the white dwarf itself. As a white dwarf cools, its interior transitions from a fluid plasma to a solid, crystalline lattice of carbon and oxygen. This phase transition is known to release latent heat. While this is accounted for in cooling models, perhaps the process is not as smooth and continuous as we assumed. Could there be localized, non-uniform crystallization events or subtle structural rearrangements within the white dwarf's interior that sporadically release additional latent heat, leading to a temporary or even sustained warming? This would imply that the inner workings of a white dwarf are far more dynamic and less perfectly crystalline than our current models predict. Alternatively, the sudden temperature increase might well point to an external heating source, currently beyond the capabilities of our telescopes to directly image. Could this white dwarf be subtly accreting extremely diffuse, cold interstellar gas and dust, so tenuous that it's invisible to us, yet just enough to provide a continuous source of energy as it falls onto the white dwarf's surface? The gravitational potential energy released by even a small amount of mass falling onto a white dwarf is immense, and if this accretion were continuous over long periods, it could theoretically provide the observed warming. However, such an accretion process would typically produce other detectable signatures, such as X-ray emission or changes in the white dwarf's spectral lines, which are not consistently observed. Another more exotic external possibility involves the white dwarf passing through a region of space with unusually high concentrations of other, non-baryonic matter, or even interacting with a localized dark energy field in an unprecedented way that subtly transfers energy to the star. This would push the boundaries of what we understand about the interaction between stars and the fabric of space-time itself. The sudden temperature increase is not merely a curious data point. It's a profound challenge to our deepest assumptions about stellar physics, urging us to explore whether these cosmic embers might yet hold active secrets capable of defiance against the cold, quiet march of cosmic time. Beyond the perplexing phenomenon of a white dwarf subtly growing warmer, we now arrive at our 25th and final profound mystery for today, the echoing radio pulse. Imagine standing in a vast, empty canyon, shouting, and then hearing your voice bounce back to you not just once but multiple times, each echo arriving at a precisely predictable delay. That's precisely what astronomers have observed emanating from a particular white dwarf. This isn't just a sporadic burst of radio waves like our earlier hello from beyond signal. Instead, it's a clear initial radio pulse followed by distinct, fainter echoes, arriving at perfectly regular, timed intervals. This pattern is definitive, a cosmic reverberation that unequivocally suggests the original signal is hitting something out there in space and bouncing back, a celestial ping-pong game providing tantalizing clues about unseen structures. What makes this observation so utterly baffling is that the nature of this reflecting body and its relationship to the white dwarf remains a profound mystery, potentially hinting at complex systems around these stellar remnants that defy our current understanding of stellar evolution and planetary dynamics. It's like finding a meticulously crafted acoustic chamber in the middle of nowhere with no discernible architect, prompting us to ask, what cosmic mirror is faithfully returning these faint whispers from the void? The diagnostic power of this echoing radio pulse lies in the precise timing of the echoes. Just as a sonar system can map the ocean floor by measuring the time it takes for sound waves to return, these radio echoes give astronomers a unique opportunity to probe the environment around the white dwarf. The delays between the initial pulse and its subsequent echoes can be used to calculate the distances to the reflecting surfaces, and the faintness of the echoes provides clues about the reflective properties of whatever is out there. If the echo came back once, it might suggest a single, large reflecting surface, but the multiple, regularly spaced echoes point to a more complex structure, perhaps a series of concentric rings or multiple orbiting bodies, each contributing a slightly delayed reflection. This highly structured and repeatable pattern rules out random interstellar gas clouds or chance alignments of distant objects. It suggests a fixed, orbiting, and substantial reflector, a kind of cosmic whisper chamber whose geometry remains stubbornly out of sight. The sheer regularity and persistence of these echoes mean that whatever is causing them is stable and in a predictable orbit around the white dwarf, acting as a natural, albeit unseen, radar target. This precise arrangement fundamentally challenges our understanding of the relatively stable, quiet environment we typically expect around dead stars that have long since moved past their planet-forming days. One of the most compelling and perhaps most exciting hypotheses put forward to explain this echoing radio pulse is the presence of a complex planetary system, or at least a significant portion of one, that somehow survived the tumultuous death throes of the white dwarf's progenitor star. Imagine a series of planets or even massive planetary fragments orbiting the white dwarf, each acting as a reflective surface for the radio pulse. The different delays in the echoes would then correspond to the different orbital distances of these bodies. If this were the case, it would be a monumental discovery, proving that planetary systems can not only survive stellar evolution into a white dwarf, but also retain a complex multi-body architecture. This would completely revolutionize our understanding of planetary habitability and the longevity of solar systems, suggesting that life might have an even longer window of opportunity to evolve around these long-lived stellar remnants. However, detecting these planets directly through conventional means like transit methods or radial velocity measurements has proven incredibly difficult, largely due to their potentially small size, faintness, or unfavorable orbital inclinations relative to our line of sight. The echoes are providing a gravitational fingerprint of their presence even if we cannot see them. Alternatively, the echoing radio pulse could be reflecting off an unusually massive and extended debris disk, perhaps one composed of large, reflective solid bodies rather than just fine dust. While we've discussed infrared excesses caused by dust, a debris disk capable of producing such clear and multiple radio echoes would need to be far more substantial, perhaps containing numerous large planetesimals or even shattered remnants of a full-sized planet, each acting as a distinct reflector. This would be a more violent scenario, implying a white dwarf that is actively dismantling a large object in its vicinity, creating a vast field of reflective rubble. The precise nature of this debris, whether it's rocky, metallic, or even icy, would significantly impact its reflective properties at radio wavelengths, adding another layer of complexity to the puzzle. The fact that these echoes are so clear and distinct rather than a smeared-out return suggests that the reflecting surfaces are relatively well-defined and not simply a diffuse cloud. This echoing radio pulse is not just a quirky acoustic phenomenon. It's a profound cosmic sonar ping, challenging us to consider whether the silent, dark remnants of dead stars are far from empty and might indeed be surrounded by complex, hidden worlds or vast fields of shattered cosmic debris, silently orbiting and reflecting the whispers of their dead suns. These 25 unexplained signals from white dwarfs are more than just isolated astronomical curiosities. They represent a profound tapestry of cosmic riddles woven into the very fabric of our universe. Each anomaly, from the baffling hello from beyond burst to the echoing radio pulse, casts a long shadow of scientific uncertainty over our most fundamental understanding of how stars live, die, and influence the cosmos around them. They challenge our established models of stellar evolution, pushing the boundaries of what we thought was possible in the extreme physics of degenerate matter and forcing us to reconsider the ultimate fate of sun-like stars. These stellar ghosts, once thought to be serenely cooling into oblivion, are proving to be anything but silent, actively broadcasting a litany of perplexing messages that defy simple categorization and demand entirely new theoretical frameworks. The collective impact of these 25 mysteries forces us to grapple with some of the most profound questions in astrophysics. What do these signals truly mean, not just individually but synergistically? Are they merely statistical anomalies, rare instances of physics pushed to its limits under extreme conditions that we haven't fully modeled? Could they be the lingering remnants of unknown cosmic events, echoes of cataclysms or interactions so subtle or so rare that their signatures are only now being detected by our increasingly sensitive instruments? Or just perhaps could they be something far grander, something we haven't even dared to imagine? Could they be indications of new physics, entirely different forms of matter or energy interactions, or even the subtle machinations of advanced civilizations operating on scales beyond our current comprehension? The possibilities, however speculative, ignite the imagination and underscore the vastness of what remains unknown in our universe. The implications of these findings extend far beyond academic interest, touching upon our very conception of the universe and our place within it. If white dwarfs thought to be inert can exhibit such complex and unexpected behaviors, it means the universe is far more dynamic and unpredictable than our current models suggest. It could mean our cosmic clocks are off, our understanding of galactic history incomplete, and our search for life perhaps misdirected. The very quiet corners of space, once deemed barren, might be teeming with active, puzzling phenomena that hold the keys to entirely new branches of science. These signals compel us to remain humble in the face of the cosmos, recognizing that every solved mystery often unearths a dozen more profound questions. So, what are your thoughts on these 25 cosmic enigmas? Do you lean towards exotic physics, undiscovered natural phenomena, or something else entirely? Share your insights and wildest theories in the comments below. We love hearing your perspectives and engaging in these cosmic conversations. If you found yourself as captivated and intrigued by these mysteries as we are, please smash that like button. It truly helps us bring more of these deep dives into the unexplained wonders of our universe. And don't forget to subscribe to the channel and hit the notification bell so you won't miss our next journey into the unknown. Until next time, keep looking up and remember, the universe is always more mysterious and awe-inspiring than we could ever fathom.